a 1995 ahsmE problem 29, and this is what it says. So for how many three-element sets, order doesn't matter, of positive integers a comma b comma c, is it true that a times b times c is equal to 2310? The positive integers a, b, and c are distinct. So immediately the thing that jumps out at me is that all the numbers multiply to 2310, and as soon as I see that, I think of just prime factorization, So, you know what? First, let's go ahead and do that. 2310 is equal to 231 times 10. Now, can we break down both of these numbers further? Well, let's just try applying a random divisibility rule, like 3. So, if a number has to be divisible by 3, the sum of the digits also has to be divisible by 3. So, 2 plus 3 plus 1 is 6, and 6 is divisible by 3. So 231 should be divisible by 3. So 231 divided by 3 is, I'm going to do it in my head, it's 77. And can we also break down 10? Yes, we can break that down as well into 5 times 2. So 2310 is equal to 77 times 3 times 5 times 2. Can we break down 77? Yes, into 7 times 11. So 2310 is equal to 7 times 11 times 3 times 5 times 2. But how does this help us at all? I mean, it literally says that for how many three-element sets of positive integers is this true? And we have 5 elements over here. Well, that's because we fully haven't really finished the problem. So from here on out, I like to use like a little thinking strategy, I guess you could call it, that instead of just thinking of them just A, B, and C as just like integers themselves, I like to think of them as boxes. So they would be classified to me as box A, box B, and box C. As you can see, whenever you put it in this format, of this box format, now it just jumps out at you that you can just sort these numbers into these boxes, and no matter what happens, they're always going to multiply to 2310. So for 7, we have 3 choices. We can put in box A, box B, and box C, and so on for all the other numbers. And since we have 5 positive integers, that would be 3 times 3 times 3 times 3 times 3, which is equal to 3 to the 5, which is also known as 243. Now, since order doesn't matter, what we want to do now is turn this from permutations into combinations. And in order to do that, we have to divide by the amount of ways we can arrange these 3 elements. Now, since we have 3 different elements, or just, 3 elements, we can arrange them in 3 factorial ways. And by that, that's 6, and by that I mean we can do ABC, ACB, BAC, BCA, CAB, and CBA. Those are all the 6 ways we can arrange this 3-element set. So, since we have 3 factorial equals 6, now we just divide 243 by 3 factorial. So 243 divided by 6. But this is going to result in the decimal. I'm pretty sure it's 40.5, but you can check for yourself because it's a decimal. And it's bad that this is a decimal because it's asking us how many 3-element sets are there, right? And is it possible for us to have 40.5 3-element sets? No, that's not possible. So what that means is that we did something wrong, or we're just missing a part of the problem. So let's think about this again. 3-element sets, order doesn't matter, positive integers, ABC. Is it true that A times B times C equals 2310? No, I don't think it's in this first question over here. I don't really think that's it. The positive integers A, B, and C are distinct. Well, what are the situations when they're not going to be distinct? Well, let's think about this. What if we had 7 over here, and something else over there? And then, I don't think it works that way because, well, we only get to put a number in a box once. We can't just put the number in box A and then immediately take it out, put it back in box B, or just duplicate it and put it in different boxes. No, we can't do that. So maybe it's like something else, like an edge case. And by edge case, I mean just a case that you wouldn't really expect, that just like doesn't align with the problem. So let's think about that. Well, numbers that are associated with edge cases are often 1, 0, and there are many other numbers, but for now, we're just going to use 1 and 0 because we know negative numbers aren't allowed, right? So let's try out these numbers. 0. I don't think we can bring that in the problem because then that's just going to result in 0 as well for our answer. So let's cross that out. But what about 1? Well, we could have 1 in one slot and then numbers over here that multiply to 2, 3, 1, 0. That's not really weird because those numbers are all distinct. But what if we had 1, 1 and then 2, 3, 1, 0? You might be asking, how is that possible? That's because there is a situation where we put all the numbers into one box. So we could put all these in a box A, all these in a box B, and all these in a box C. There are 3 different situations like that. Notably being 1, 1, 2, 3, 1, 0, 1, 2, 3, 1, 0, 1, and 2, 3, 1, 0, 1, 1. So that means that we shouldn't have included those 3 scenarios. So we'll subtract that number from 243, and we ended up getting 240. Is that divisible by 6? Yes, that does give us a proper integer now. So we now know the answer to the problem is 240 divided by 6, which is 40. So our answer is that there are 43 element sets of positive integers a, b, c, where it is true that a times b times c is equal to 2, 3, 1, 0.